Hi, this is educator.com, and we are here to talk about sine and cosine functions. So I'll start out by giving you the definitions and kind of the master formulas, and then we'll go through and work on a bunch of examples. The definition of sine and cosine of an angle is you start out with the axes and the unit circle. So it's important to know that this is a unit circle, meaning the radius is 1. What you do is you draw that angle in standard position, meaning it has one side on the x-axis, and there's theta right there. Then you look at the coordinates of the point, the x and y coordinates on the unit circle. So the x coordinate is, I'll go over that in red. That's the x coordinate right there. And the y-coordinate, that's the one in blue. And those coordinates are, by definition, I wanted to do the cosine in red. Cosine of theta, and then in blue, sine theta. So that's the definition of what an angle is in terms of coordinates on the unit circle. If you know what the angle is, you try to figure out what its x-coordinate and its y-coordinate are, and that's called the cosine of theta and the sine of theta. Now, we'll see some more examples of that later so that you'll know how to actually compute the cosine and sine, but the definition just refers to those coordinates. The most common use of sine and cosine probably is in terms of right triangles. So let me draw a right triangle. Right triangle just means a triangle where one of the angles is a right angle, a 90-degree angle, or in terms of radians, pi over 2. And what you do is you let theta be one of the angles that is not the 90-degree angle, so one of the other angles. And then you label each one of the sides in terms of its relationship to theta. So the one next to theta is called the adjacent side. The one opposite theta is called the opposite side. And the long side is called the hypotenuse. And then we have the master formula for right triangles, which is that the sine of theta is equal to the length of the opposite side divided by the hypotenuse. The cosine of theta is equal to the adjacent side divided by the hypotenuse. And the tangent of theta, which is something we haven't officially defined yet, so we'll learn about tangent in a later lesson, but I just want to give you the right triangle formula now because we're going to try and remember them all together. The tangent of theta, when we get to it, will be the opposite side divided by the adjacent side. So we don't want to worry too much about tangent now because we haven't learned about it in detail yet. I'll get to those later. But if you put all these formulas together, it's kind of hard to remember the relationships. So people have come up with this acronym. Sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. And if you kind of read that quickly, people call it SOHCAHTOA. And if you talk to any trigonometry teacher in the world or any trigonometry student in the world, they should have heard the word SOHCAHTOA because that's kind of the master formula that helps you remember all these relationships. They're kind of hard to remember on their own, but if you remember SOHCAHTOA, you won't go wrong. If you have trouble remembering that, there's a little mnemonic device that people also use. Some old horse caught another horse taking oats away. So if you remember that sentence, if that's easier for you to remember than SOHCAHTOA, then you can remember all of these formulas. There's another definition that we need to learn, which is that a function is odd if f of negative x is equal to negative f of x. So let's figure out what that means. We're going to talk about odd and even functions. Let me give you an example here. F of x is equal to x cubed. Well, let's try f of negative x here. I'm going to check this definition of odd function here. So f of negative x, that means you plug negative x into the function. So that's negative x quantity cubed, which is negative 1 cubed times x cubed. Negative 1 cubed is negative 1, so that's just negative x cubed. And that's negative of the original f of x. So for x cubed, f of negative x is equal to negative f of x, which means it's an odd function. Now, there's a way to check this graphically. If you graph f of x equals x cubed, it looks something like this. And that means that if you look at a particular value of x, and you look at f of x there, and then you look at negative x, f of negative x is equal to the negative value of f of x. So that's what it looks like graphically. What it means is that the graph has what I call rotational symmetry around the origin. If you put a big dot on the origin, and if you spun this graph around 180 degrees, it would look the same, and that's because of f of x and f of negative x being opposites of each other. So if you spin the graph around 180 degrees and it looks the same, if it looks symmetric with itself, that's called an odd function. The way you remember that odd functions have that property is just remember x cubed, x to the third, because 3 is an odd number and x cubed is an odd function. So if something kind of has that property that x cubed has, then it's an odd function. The companion definition to that is that f is even if f of negative x equals f of x. So the difference there was that negative sign on the odd definition, no negative sign here on the even definition. So let me give you an example of an even one. Let's define f of x to be x squared. Well, f of negative x is equal to, you plug in negative x into the function, so negative x quantity squared, but that's just the same as x squared, which is the same as the original f of x. So f of negative x is equal to f of x. That checks the definition, so it's even. And of course, you'll notice that x squared, the 2 there is an even number. That's no coincidence. That's why we call even functions even, is because they sort of behave like x squared. If you graph those, let me graph x squared for you. That's a familiar parabola that you learned how to graph in the algebra section. And if you take a value of x and look at f of x, and then you take negative x, f of negative x is not negative f of x, it's f of x itself. It's the same value as f of x itself. So you get this f of negative x is equal to f of x. So what that means is that you have a kind of symmetry across the y-axis with even functions. If a function is symmetric across the y-axis, if it looks like a mirror image of itself across the y-axis, then that's an even function. So that's why I say it has mirror symmetry across the y-axis. That's what an even function looks like. And there's a common misconception among students. People think, well, with numbers, every number is either odd or even. People think, well, every function is odd or even, and that's not necessarily true. Just for example, here's a line, but that is not that doesn't have rotational symmetry around the origin, nor does it have mirror symmetry around the y-axis. So that function, this line, is not an odd or an even function. So it's a little misleading. People think every function has to be an odd or an even function. That's not true. It's just true that some functions are odd, some functions are even, some functions are neither one. So we'll practice some examples of that. But first, we're going to look at some common angles, and we're going to figure out what their cosines and sines are. So let me draw a big unit circle here. So that's a circle of radius 1. And let's remember where these angles are. 0, of course, is on the positive x-axis. So here's the x-axis. Here's the y-axis. There's 0. Pi over 2, remember that's the same as a 90-degree angle. That's a right angle, so that's up there, pi over 2. Pi is over here. That's 180 degrees. 3 pi over 2 is down here. And 2 pi is right here. So we want to find the cosine and sine of each one of those angles. Now remember, cosine and sine, by definition, are the x and y coordinates of those angles. So what are these x and y coordinates? Well, the 0 angle, its x coordinate is 1, and its y coordinate is 0. So that tells us that cosine of 0 is 1. And sine of 0 is 0. Pi over 2 is up here. And so its cosine is the x-coordinate. Well, the x-coordinate of that point is 0. The y-coordinate is 1, and so that's the sine of pi over 2. Pi is over here at -1, 0, so that's the cosine and sine of pi. Cosine of pi is -1. Sine of pi is 0. And finally, 3 pi over 2 is down here at 0, -1, so that's the cosine and sine of 3 pi over 2. Cosine is 0. Sine of 3 pi over 2 is -1. And one more. 2 pi is back in the same place as 0, so it has the same cosine and sine. Cosine of 2 pi is 1. Cosine of 2 pi, sine of 2 pi is 0. So that's how you figure out the cosine and sines of angles, is you graph them on the unit circle, and then you look at the x and y coordinates. The x-coordinate is always the cosine, and the y-coordinate is always the sine. By the way, these are very common values: 0, pi over 2, pi, 3 pi over 2, and 2 pi. You should really know the sines and cosines of all of these angles by heart. They come up so often in trigonometry contexts that it's worth memorizing these things and being able to sort of regurgitate them very, very quickly. If you ever forget them, though, if you ever can't quite remember what the cosine of pi over 2 or the sine of 3 pi over 2 is, then what you do is you just draw yourself a little unit circle and you figure out what the x and y coordinates are, and you can always work them out. So it's worth memorizing them to know them quickly, but if you ever get stumped or you aren't quite sure, just draw yourself a unit circle and you'll figure them out quickly. We're going to use these values, so I hope you will remember these values for the next example. In the next example, we're being asked to draw the graphs of the cosine and the sine function. So let's remember what those values are, and we're going to label all the zeros and the maxima and the minima of these functions. So let me set up some axes here. And I'm going to label my x-axis in terms of multiples of pi. And the reason I'm going to do that is because we're talking about cosines and sines of multiples of pi. So we're really talking about radians here. So that's pi, that's 2 pi, that's pi over 2, and that's 3 pi over 2. That's 0, of course. The y-axis I'm going to label as 1 and -1. And I've set up my scale here. Remember that pi is about 3.14, so it's a little bit bigger than 3. So I've set up my scale here so that the pi is about a little bit beyond 3 units on the graph. I'll extend it a little bit on the left here as well. So we've got negative pi, I draw that around -3, and negative pi over 2. And now I want to graph the sine and cosine function according to those values that we figured out. Remember that the sine and cosine function correspond to coordinates of angles on the unit circle. So sine and cosine, remember, are the x and y coordinates of angles on the unit circle. Now, those coordinates will never get bigger than 1 or smaller than -1. So that's why on my y-axis I only went up to -1 and 1, because the coordinates will never get bigger than -1 and 1. So let me start out with the cosine function. I'll do that one in blue. Y equals cosine x. So we'll remember the values that we learned in the previous question. Cosine x, cosine of 0 is 1. Cosine of pi over 2 was 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is up at 1 again. And so what you get is this smooth curve and after 2 pi, remember, after you circle 2 pi radians, then everything starts repeating. So what happens after 2 pi is that it repeats itself. And it repeats itself in the negative direction as well. And so now we know what the graph of cosine x looks like. I'll do the sine graph in red. And remember that sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi was 0 again. Sine of 3 pi over 2 was -1. Sine of 2 pi is 0. I'm doing these from memory, and hopefully you remember these values as well. But if you ever can't remember these values, you know you can always look back at the unit circle and figure them out again just from their coordinates. So the sine graph, I'm going to connect these up into a smooth curve. And it repeats itself after this. And it repeats in the negative direction as well. So that's what y equals sine x looks like. It actually has the same shape as cosine x, but it's shifted over on the graph. Now we're asked to label all zeros and maxima and minima. Let me go through and label the zeros first. This is, on the cosine x, this is pi over 2, 0. That's a 0 right there. There's one right there, 3 pi over 2, 0. And this one, even though I haven't labeled it on the x-axis, is actually 5 pi over 2, 0, because it's pi over 2 beyond 2 pi. Negative pi over 2, 0. So those are the zeros of the cosine graph. The maxima, the high points, remember cosine and sine never get bigger than 1 or less than -1. So anytime it actually hits 1, it's a maximum. So there are the two maxima at 0 and 2 pi. The minimum value is -1. So there's pi -1. And the next one would be at 3 pi, -1. There's one at -pi, -1. And now let me do the zeros of the sine graph. There's one, 0, 0, -pi 0, and pi 0, 2 pi 0. The maximum value would be 1, and that occurs at pi over 2. And again at 5 pi over 2. And the minimum value would be at 3 pi over 2, where the sign is -1. Remember, sine and cosine never go outside that range, -1 to 1. And at -pi over 2. So all of these values you should pretty much have memorized. They're the sort of simplest values, the easiest ones to figure out of sine and cosine. So let's try an example where we're using these trigonometric functions in a triangle. What we're told is that a right triangle has short sides of length 3 and 4, and we're asked to find the sine, cosine, and tangent of all angles in the triangle. Remember, I haven't really explained what tangent is yet, but we did learn that formula, SOHCAHTOA, so that's what we're going to be using here. So the first thing we need to figure out here is what the hypotenuse of this triangle is, and we have the Pythagorean theorem that says h squared is equal to 3 squared plus 4 squared, which is 9 plus 16, which is 25. And so that tells us that the hypotenuse must be 5. So now we're going to find the sine, cosine, and tangent of each one of these angles. So let's figure out this angle first. I'll call it theta. Sine of theta, remember SOHCAHTOA. Let me write that down for reference here, SOHCAHTOA. Sine theta is equal to opposite over adjacent. So that's 4. That's the opposite side from theta over, sorry, I said sine theta is opposite over adjacent. Of course, sine theta is opposite over hypotenuse, and the hypotenuse is 5. So sine theta there is 4/5. Cosine theta is equal to adjacent over hypotenuse. Well, the side adjacent to theta is 3. Hypotenuse is still 5. And tangent of theta is equal to opposite over adjacent. Again, we haven't really learned what the tangent means yet, but we can still use SOHCAHTOA. The opposite over adjacent is 4/3. Let me call the other angle here phi. Sine of phi is equal to the opposite over the hypotenuse, so 3/5. Cosine of phi is equal to adjacent over hypotenuse. The adjacent angle or side to phi is 4. And tangent of theta is equal to the opposite over adjacent, so that's 3/4. And finally, we have the right angle here. I'll call that alpha. We can't really use SOHCAHTOA on that, but I know that sine of alpha, alpha is a 90-degree angle, or in terms of radians, it's pi over 2. And the sine of pi over 2 we learned before is 1. Cosine of alpha is cosine of pi over 2. And we learned that the cosine of pi over 2 before was 0. And finally, tangent of alpha is tangent of pi over 2, and we haven't really learned about tangent yet, and in particular we haven't learned what to do with the tangent of pi over 2, but we'll get to that in a later lecture and we'll learn that that's actually not defined. So we can't give a value to the tangent of pi over 2. So all of these angles were things we worked out just using this one master formula, SOHCAHTOA. That tells you the sine, cosine, and tangent of the small angles in the triangle. The right angle doesn't really apply to SOHCAHTOA doesn't really apply to the right angle, but we already know the sine and cosine of a right angle, of a 90-degree angle, because we figured them out before. So we'll try some more examples here. I want to try graphing the function sine of x plus pi over 2 and cosine of x minus pi over 2. And then I want to determine whether these functions are odd or even or neither one. Well, something that's really good to remember here from your algebra class or from the algebra lectures here on educator.com is that when you have a function and you try to graph f of x minus a constant, what that does is it moves the graph of the function over by the amount of the constant. So that's very useful in a trigonometric setting. Let me start out by graphing f of x equals sine x. And we did that in a previous example, and I remember what the sine graph looks like. It starts at 0, it peaks at pi over 2, it goes back to 0 at pi. It bottoms out at at 3 pi over 2 at negative 1, and then it goes back to 0 at 2 pi. So what I graphed there was just sine x. I haven't introduced this change yet. What I'm going to do in blue now is the sine of x plus pi over 2. What that's going to do is going to move the graph over pi over 2 units. But remember, there was a negative sign in there that I don't have here. So this is really like sine of x minus negative pi over 2. So it moves the graph over negative pi over 2 units, which means it moves it to the left pi over 2 units. So I'm going to take this graph and I'm going to move it over to the left pi over 2 units. So now it's going to start at negative pi over 2, come back down at pi over 2, bottom out at pi, and come back to 0 at 3 pi over 2. So there's negative pi over 2, 0, pi over 2, and it comes back at 3 pi over 2. So that's what our graph of sine of x plus pi over 2 looks like. And then the question is that odd or even or neither? Well, remember, there's a graphic way to look at the graph of a function and determine whether it's odd or even or neither. An odd function, remember, has rotational symmetry. An even function has mirror symmetry across the y-axis. Well, if you look at this graph, it certainly doesn't have rotational symmetry, because if you tried to rotate it around the origin, it would end up down here, and that would be a different graph. However, it does have mirror symmetry around the y-axis. So because it's mirror symmetric around the y-axis, sine of x plus pi over 2, f of x, is an even function. because it has mirror symmetry. Oops. Mirror symmetry across the y-axis. Okay, let's move on to the next one. Cosine of x minus pi over 2. Again, I'm going to start with the basic cosine function that we learned how to graph in a previous example. Set up my marks here. There's pi, there's 2 pi, pi over 2, 3 pi over 2, 0, negative pi over 2. Now cosine, at 0 it's 1, then it comes down to 0 at pi over 2, bottoms out at negative 1 at pi, comes back to 0 at 3 pi over 2, and by 2 pi it's back up at 1. So what I've just graphed there in black is cosine x. I haven't tried to introduce the shift yet, but what we want to do is to graph cosine of x minus pi over 2. So that's like saying the c up here is pi over 2. That's going to shift the graph pi over 2 units to the right. Because it's minus pi over 2, it shifts it to the right. So we take this graph and we move it over to the right, pi over 2 units. Drew that a little too high. Let me flatten that out a little bit. What we have there is the graph of cosine of x minus pi over 2. And of course it keeps going in the other direction there. And we see actually, if you look carefully, cosine of x minus pi over 2 actually turns out to be the same graph as sine of x. So that's a familiar function if you remember those graphs. Again, we're being asked whether the function is odd or even or neither. And for odd, we're checking rotational symmetry around the origin. And look at that. If you rotate the graph 180 degrees around the origin, what you'll end up with is exactly the same picture. So g of x is an odd function because it has rotational symmetry around the origin. Is it an even function? Does it have mirror symmetry around the y-axis? And no, it doesn't, because it has this kind of bump on the right-hand side, and it doesn't have the same bump on the left-hand side. So it's not an odd function. Or sorry, it's not an even function. It's just an odd function. So what we did there was we started with the sine and cosine graphs that we remember. It's worth memorizing the basic sine and cosine graphs. And then we examined the shift that each one introduced. Each one got shifted pi over 2 units to the right or left, and then we drew the new graphs, and then we looked back at them and we checked what kind of symmetry did they have. Do they have rotational symmetry or mirror symmetry? And that tells us whether they're odd or even.